In the last lecture, I kind of wanted to go over again what we discussed. Okay, so I wanted to first kind of recap the main points from diffusion control problems. Okay, so here, when we're considering something that's like a diffusion process, like a stochastic differential equation like this one here, okay, we have a drift term which we can influence with our actions, and we have a diffusivity term which we could also influence with our actions. Okay, we might want to try to change the state of this process so as to maximize or minimize some objective. Okay, like here. Okay, and I've written this over a finite time that we want to maximize the expected sum of costs or integral of costs with some discount factor here, alpha. Okay, now this could go for infinite time or finite time. Okay, one thing that we notice, if this went over infinite time here and the cost function didn't depend on time, then we've got something that's somehow homogeneous with time. Okay, so we could consider just the cost function L here rather than have to worry about things like L of t, which is this objective started from time tau in this case. Okay, so we can either look at functions of this form. We can look at functions of this form, L of x, where x is the state of our stochastic differential equation, and when things depend on time, we might look at L of t of x. Okay, and for each of these, we can derive a Hamilton-Jacobi Bellman equation, okay, which is the diffusion analog or continuous time analog of the Bellman equation for a Markov decision process. Okay, so what does that look like? Well, it looks like this. Okay, essentially we have the cost function. Okay, and I'll notice I should probably delete one of these terms. Actually, I'll delete this one, I think. Okay, we have the cost function. Okay, actually I'll delete this one. I shouldn't have this one here, that's my fault. We have the cost function minus the discount rate times our function at L. Okay, and then we have essentially the drift term that we would get from Ito's formula. Okay, so whenever we write down the HJB equation, the way to remember it is that 0 equals the minimum or maximum over the actions we can take, then the instantaneous cost, okay, then minus the discount rate times our value function L, okay, right, and then plus the drift term from Ito's formula. Applied, and when I apply Ito's formula, I apply it to L of x of t. Okay? Right, that's the kind of basic form that we get in order to derive the HJB equation. Okay? Now, then what we went on to do is to look at this in the context of sort of portfolio optimization. So I'll just click on that here. Okay, so we looked at a specific type of example, okay, where we could either invest in a single stock, okay, which obeyed a geometric Brownian motion, or we could put our money into some bank account which gave us a fixed rate of interest, R. Okay, and here we see that if we choose NT, a number of stocks, and CT, a rate of consumption, okay, then our wealth evolves according to this stochastic differential equation. All right. Okay, and we can apply the same HJB equation in this case, okay, and that is derived here, okay, And again, the idea is to essentially look at the drift term that you get from Ito's formula, okay, and add that on to the instantaneous cost minus the discount factor times to the value function again. Okay, so that was essentially the main mechanism that we used. And now what I wanted to kind of cover is how do we do this in a case where there are many assets that we can invest in. Okay, so it's just a slight generalization of the previous case. All right, so I'll kind of recap that now. Okay, so just get to the beginning of this section. Okay, so we're going to look at Merton portfolio optimization with multiple assets. Okay, and I want to show you that it's not a big extension of the case where there's just a single asset that we can invest in. Okay, so we note how. We're going to note how the above results extend to the case where there are many assets. Okay, we now suppose that there are D assets that can be invested in, and they obey a stochastic differential equation. Okay, so a bit like the geometric Brownian motion that we had before, we've got something that grows geometrically with some diffusion term, okay, and some drift mu I. Okay, and the kind of variability, okay, is given by a sum of independent Brownian motions. Okay, and this allows for there to be correlations between the different assets. Okay, so they might be driven, for example, by the same Brownian motion, in which case they're completely correlated with one another. Okay, all right. Now, just like before, if I let n of t be the number of stocks that I've bought, okay, of type I, okay, then ni be the number of stocks of asset I that I bought, then S of I t times n of I t is the amount of wealth that I have in asset I. Okay, and so if we take the dot product of n with S, okay, we end up with the total amount of wealth that we have invested in stocks. Okay, so if I take my wealth minus the wealth invested in stocks, okay, that is the amount of money that I put in the bank account, and that receives this interest rate R. Okay, then this is going to give us the change in our stocks. Okay, so the number of assets I have times by the change is going to give me the change in my wealth due to the holdings that I have in stocks, and then I minus off again the rate of consumption, which is ultimately the thing we want to maximize. Okay. Okay. We're also going to define theta to be the wealth in asset I at time t. Okay. Okay, and our job is to maximize the following objective, which is to maximize the utility that we get from our consumption. Okay, applying some discount factor rho, okay, or e to the minus rho. Okay, and we want to maximize that over all time. Okay, and now I want to show how the case that we covered before for a single asset applies to the case where we've got multiple assets. Okay, so the first thing I want to show is that the HJB equation for this is of the following form. Okay, so let's go through that. Okay, so let's answer that. Okay, so we want to essentially use the same form as we discussed before. We want to find out the drift of, in this case, we want to look at the drift of the diffusion given by V of W of t. Okay, and we know by Ito's formula, okay, that this is equal to the partial derivative of V with respect to W. Okay, plus a half the twice partial derivative of v of wt times the quadratic variation of w. Okay, and now we need to investigate a little bit what w is and how to write it out. Okay, so dw dt, as I wrote above, is equal to r lots of w, okay, minus r lots of n dot producted with s, okay, the prices of the assets or the stocks, dt, plus n, okay, ds dt, okay, minus c of t dt. Okay, now let's think about some of these terms. So really what this is just theta, okay, the sum of all the components of theta as I've defined it up here. Okay, so I'm really just summing up all these thetas and then multiplying it by r. Okay, so I could kind of rethink of this as just the vector theta multiplied by just a vector that just consists of r in each component. So I'm going to let r bar be the vector of just all r's in each component. Okay, so that's just another way of writing this at time t. Okay, we can also notice that this ds dt, okay, notice each component of that vector here has an si at the front, sit, and I'm multiplying it by nt, okay, the ith component of the number of stocks that I have in asset I. So I'm going to again end up with an ni times si for each of these terms. I'm going to get ni times si and then summed up over I. Okay, so if I collect all these terms together, what you can notice, I'm going to end up with that same theta vector again, okay, for the NISI, okay, and then applied to this bracketed term here. And notice really what I'm doing is I'm looking at sigma as a matrix, okay, to the left of that matrix I'm applying the vector theta, and to the right of that matrix I'm applying dB, okay, where that's the vector of the changes in all these independent Brownian motions. Okay, so what I'm going to end up with here is the vector theta applied to the matrix sigma, okay, and then that applied to the vector dbt, okay, plus the vector of mu's dt. Okay, so that's what all of this expression is going to give me. All right, so just collecting that together again, what I really have here, okay, is that I have collecting all the dt terms and all the dbt terms, okay, really this is equal to r of wt theta bar, okay, mu minus r, okay, so the r coming from here and the mu coming from here, okay, minus ct dt, okay, so that captures all the dt terms in here, right, and then plus the diffusion part, which is essentially this vector applied to this matrix, then applied to the diffusion terms, the Brownian motion terms. Okay, right, all right, so we've got this dwt term in here, and we also want to get the quadratic variation term. Okay, we can see from this form that we can pick that up pretty easily. So notice the w quadratic variation dt is really just going to be the square, okay, of each of these terms. So we've got a vector here, and we're just going to square up the components of that vector. Okay, so it's really theta t sigma squared dt. Okay, right, so now we can put all of this together, all right, to get to look at what the drift term of this expression is. Okay, so I'm going to essentially substitute 1 and 2 here and here, okay, and collect some of the terms together. All right, so the dv of w of t, okay, is going to be equal to, okay, so this dt times this part, okay, so r of wt plus theta t mu minus r minus ct, and all of that times by the partial derivative of v, okay, and all of that's dt, all right, and then I'm going to get a dt term for this, so I'm going to get plus a half the second partial derivative of w here, okay, and then times this, which is theta t sigma squared, and so that is going to give us all of the dt terms, all right, and then the diffusion part applied to this, okay, so I'm going to get a half second partial derivative, oh sorry, first, pardon me, no half, so then I'm going to get this term here, okay, apply to dv dbt, okay, right, that collects together all the terms, and so we've got in the square brackets here, I've got the drift term, okay, so this is the drift, this part, and then this is the diffusion part, okay. Now remember that the HJB equation is in this case it's the maximization, so the HJB equation is 0 is the maximum over the sets of actions, which in this case is the amount that I consume, and the vector of the asset portfolio that I hold, okay, then the instantaneous cost, which in this case is the utility function of the consumption, minus the discount rate applied to the value function, okay, and then I add on the drift term from Ito's formula, okay, so here it's r w t, oh sorry, I'll do lowercase w now, w plus theta applied to mu minus r minus c, okay, partial derivative of v, okay, here, plus half dw twice, okay, so second partial derivative of v times theta sigma squared, okay. Now you'll notice this is exactly the term up here, right? The only thing I've done is I've noticed that some of these terms are to do with c, not theta, so this is to do with c, and this has something to do with c, but nothing to do with theta, and I've just collected those terms together here, okay? And some of the terms are to do with theta, in particular, but nothing to do with c, so that's this term and this term, okay? And I've just collected those together here, right? And then some of the terms have nothing to do with theta and nothing to do with c, specifically this one and this one, okay, and I've collected those together at the end, okay, so that's where that HJB equation comes from. All right, now we need to kind of work with this to come up with the solution, okay. We start with the easiest of the two, okay, which is this maximization over theta, all right. So the next exercise is to essentially solve that maximization, okay? And like I said in class the other day, this isn't too hard, all right? So the thing to note is that if I did the partial derivatives of each of those terms, it would behave in a very similar way to the way I do normal differentiation. I could almost pretend that theta was just a normal random variable, okay, and then just apply chain rule in a normal way, Okay, so we did it a little bit more detailed in class where we wrote it out as the sum of different components and applied the chain rule to each of those components. But I'll just do it a little bit more quickly this time. Okay, but notice if I look at the gradient of this guy with respect to theta, okay, so I take the partial derivatives of this with respect to theta and look at that vector, and I set that equal to 0 in the normal way I would when I look for a stationary point. I take derivatives in all directions and check if those are all equal to 0, then it must be a local minimum or local maximum. Okay, in this case specifically it's going to be local maximum, okay, because this gradient is going to be negative. Okay, so if I take the partial derivatives of the term in curly brackets here with respect to theta, I'm going to get a vector mu minus r times by the partial derivative of v, okay, and then applying the sort of product rule for differentiation to either side of this, I'm going to get two lots, okay, of sigma t, sigma theta, okay, so I'm going to get sigma t, sigma theta, okay, so think of this like sigma squared. If I differentiate to sigma squared divided by 2, I just get sigma, okay, and then the second partial derivative of v, okay. Then if I set this equal to 0, notice I can now solve for theta, okay, and you can find that the form of theta that I get is exactly this, okay. Right. Now, again, if I substitute this back into this expression here, you can notice that I'll get minus 1 lots of kappa squared times this term, and then a half of that same term. So overall I'll end up with minus a half kappa squared, and then partial derivative of wv squared divided by the second partial derivative of v. And just to remember that kappa here is equal to mu minus r divided by sigma, okay, or as the vector is given by that, okay. So, okay, great. Okay, good. Or when I say sigma, I should be saying, sorry, sigma to the minus 1 here, really. Sigma minus 1. Okay, apologies. Yeah, okay, good. Right. Okay. So then, the next part that I ask you to do, and I'm kind of leaving this as an exercise to you because it includes a few too many parts of your exam solutions, okay, but you can check in a very similar way to before, okay, that we can find the solution of C star, okay, to be of this form, gamma to the minus 1 minus r divided by w, okay, and I can substitute this into my expression and get the form of the gamma the same as before. Now the reason I'm not really going through all of that is because the argument is exactly the same, okay, as in the one-dimensional case, because by solving for this theta star, I've dealt with all of the parts in this HJB equation that have a vector in them, okay, and everything we're left with is just scalars, okay, so it's going to work exactly the same as the scalar case, okay, so the previous case with a single asset to invest in, okay. So do try to go through that exercise and convince yourself that you can do that, okay? But it should be something that's quite doable, okay? Now, some definitions associated with this. So the kind of vector of assets that we hold, or the wealth that we hold, okay, has this form when we assume that our utility function is a Carroll utility. And this is sometimes called the Merton Portfolio, okay? And it gives us the amount of assets that we hold in each case, okay? And then also this kappa vector is called the market price risk vector. It's somehow looking at the benefit that we get from the drift and then readjusted according to the volatility, okay? So it depends on, you know, if we've got a large variance, okay, we have to use that to cancel out the benefit that we might have from having a large drift. Okay, so it's very similar to what we see in Markowitz portfolio optimization. Okay, right. Okay, so that's the main things I wanted to say about multiple assets. In a second, I'll go on to talk about the case where we don't have a utility function that is a carrier utility. So far we've dealt with utility functions which have a specific form. We want to look at general utility functions, and we can show that we can still solve those cases. Okay, great.